Okay, so this is the recording of where we stop. So the last lesson we talk about mechanism and we talk about some reactions are made up of more than one step and they constitute a series of individual steps which are known as the elementary steps. And these elementary steps makes up the mechanism. Okay, for those reactions which has more than one step, then we will have to assign a rate determining step. And the rate determining step will be the step which has the highest activation energy. So we're looking at our rate determining step will be the one that has the greatest activation energy. And not only that, it should also match with the experimentally determined rate equation. So it should match with your rate equation that you determine from the experiment. Okay, so let's look at some examples. Okay, so we talk about this example over here. If you remember, so I just do a very quick recap of this example. Okay, so first we have this equation, which is the overall equation. And after we have conducted an experiment, we got the experimentally determined rate equation from our data. Now, so from the mechanism, we will try to, from the rate equation, we will try to propose a mechanism that can fit this. So as we are proposing a mechanism, we may want to propose that there's two molecules of NO colliding with one molecule of Cl2. However, we all know that the probability of having three particles colliding at the same time with the correct orientation and the correct activation energy is quite low. And therefore, instead of proposing two NO and one Cl colliding to get the reaction started, we will propose a series of elementary steps. And what is very important in the elementary step is that usually it cannot be more than bimolecular. So each step cannot be more than bimolecular. So what's the meaning of that? That means, right, in each step, the number of molecules of reactants involved should not be more than 2. It can be 1, it can be 2, but it should not be more than 2 because of the low probability. Okay, so now as we are proposing the mechanism, what do we do is that, of course, we use our reactants. So we use our reactants to propose the mechanism. Okay, so for example, I have two NO and one Cl. I decide to use one NO and one Cl2 first to react to form an intermediate. So I'm using one NO reactant, one Cl2 reactant, and I let it react to form an intermediate. So what is an intermediate? An intermediate is a substance that is formed and then is consumed. So it's not present at the start as a reactant. It's not present at the end as a product. Okay, so with my intermediate, since I have to consume it and use up, so the intermediate will be the reactant in the next step. And if you look at my overall equation, I have used up one NO and one Cl2, but I have not used up one more NO, right? So I will use NO with my intermediate to form what I wanted to get, which is my product, which is the NOCl. Okay, so with that, I need to assign one of the steps as the rate determining step. In order for me to assign the rate determining step, I will have to look at the rate equation. Okay, because my rate determining step must match the rate equation. So with that, I will assign step 2 as the rate determining step. And when I first write the rate equation based on step 2 mole ratio, it will be 1 mole of NOCl2 with 1 mole of NO. Now, however, in the rate equation must only contain reactants. So this over here, being an intermediate, will have to be substituted away or substituted using the reactants. So how do I substitute the NOCl? Okay, I look at how NOCl is formed in the first step. it was formed from NO and Cl2. Okay, those who have read ahead will know that maybe you have read up before, you will be able to write a Kc expression, which is the equilibrium expression. If not, you can just, at this moment, just take a look at NoCl2. It actually came from NO and Cl2. And so I'm going to substitute NoCl2 with NO and Cl2. Okay, but of course, the correct way is to write an equilibrium constant expression. So if we look at this equation, it's a reversible reaction. I'm trying to substitute this NoCl2 using this equation. So what I can do is I can write something known as a Kc expression, whereby the Kc expression is used for a reversible reaction. When you have a reversible reaction, it is the product raised to the stoichiometric ratio over the reactants raised to the respective mole ratio. So therefore, the product will be NoCl2 raised to the power of 1, because there's only 1 mole, divided by the reactants, which is NO raised to the power of 1, because there's only 1 mole, and Cl2 raised to the power of 1, because there's only 1 mole. So, and I rearrange this Kc expression, and I make NoCl2 my subject. So the moment I make NoCl2 of my subject, I get an expression. What am I going to do with this expression is that I'm going to substitute this expression to replace the NoCl2, which was in the rate equation, because the rate equation must not contain any intermediate. It should only contain the reactant. So I'm going to substitute. As a result of the substitution, the substituted rate equation will look like this. And Kc times K1 is still another K, right? So there will be a K rate constant, and the rate constant is a result of Kc times K1. And then you have our NO appearing twice, so NO squared, Cl2 appearing once, so it's Cl2. So I got my rate equation. And what do we do? Do we accept the rate equation? Before we accept, we need to compare. Is it the same as our experimentally determined rate equation? So you can see it is the same. So therefore, my mechanism is logical, because the rate determining steps matches the rate equation. And not only that, when I sum up step 1 and step 2, I should be able to get my overall equation. Okay, so let me show you the second part, which is when I sum up step 1 and step 2, I should be getting the overall equation here. Okay, so what do you do is that if you sum up these two equations, you will find that the intermediate cancels out. And what you're left with is there are 2 NO plus Cl2, and that gives me 2 NoCl, and it matches my overall equation. Okay, so we will look at one more example. Example over here. I have 2 ozone breaking down into 3 oxygen molecules. So that's the overall equation. So my mechanism that I'm suggesting is that during the first step, 1 ozone breaks down to form oxygen and molecule and oxygen atom. And this is my product. Can you see this is my product? Right over here, this is the product. And it's my reactant. Okay, so O atom here is an intermediate. So it was produced in the reaction and it has to be consumed. So the next step, what I will do is that I will bring the intermediate, I will use up the intermediate. And if you look at the number of reactants, I should have 2 ozone, but I only use 1. So I'm going to bring 1 more ozone here and let them react and form 2 oxygen molecules. So when I sum up these 2 steps, I will get the overall equation because the intermediate cancels out. And I have 2 ozone giving me 3 O2. All right. Now, so based on that, if we look at the rate determining step, which is the slow step, my rate equation will be this. rate equals to KO3 to the power of 1, because in the rate determining step, there's only 1 mole of ozone as the reactant. Okay, so if we have something like this, which is a unimolecular, that means there's only 1 molecule involved in the rate determining step. So you can see that in the first step, oxygen atom is formed and then it's used up, and therefore we call it the intermediate. Okay, now when I'm sketching an energy profile diagram for a multi-step reactions, the number of this, I call that camel harms. Okay, the number of harms that you will get and the number of transitions that you get depends on how many steps. So if you have a typical one-step reaction, then it will look like this. If it's 2 steps, then you should expect to see 2. And if it's 3 steps, then you will expect to see 3. Okay, so there should be, in this case, since it's a 2-step reaction, then there should be 2 transition states. Now, how do we assign which one is the, how do we show that it's a slow step in our drawing? A slow step usually has the greatest activation energy. So when I'm drawing my energy profile diagram, I will need to make sure my EA1 is much bigger than the corresponding EA2. All right, so just to take note, EA is drawn from the reactant to the transition state. So therefore, EA1 is from reactant to the transition state. And for EA2, the reactant was the intermediate. So therefore, it was from here to the transition state. So after the first reaction, I form an intermediate, which serves as a reactant in the second step of the reaction. Okay? Okay, so that's for energy profile diagram. So given the decomposition of peroxide from the proposed mechanism, find the rate equation. So this is the proposed mechanism. My eyes should be looking on the slow step, and the rate equation should be based on the slow step. So do I write H2O2, sorry. Rate equals to K, H2O2, 1, I minus 1. Because in the slow step, I'm seeing 1 H2O2 and 1 I minus. Right? Then the question is, but I don't see any I minus in the overall equation. It's not there. So can I put it in my rate equation? So let you think for a while first. So H2O2 is in the equation, but I minus is not in the overall equation. So can I put it in the rate equation? Okay, think about it. So what we say about rate equation is that the rate equation should not contain any intermediate. Okay, so in this case, before we can tell whether I minus should be in the rate equation, we need to know whether I minus is an intermediate, right? So intermediate is something that is formed and consumed. But I minus here is not something that is formed. It's something that you put in. And at the end of the day, you get it back. So what is something that you put in and at the end of the day, you get it back? That is catalyst. So I minus over here is having the role of a catalyst because you added in and it's regenerated. Okay, so the rule of the rule states that our rate equation should not contain any intermediate, but catalyst is fine because catalyst is something that you put in. Okay, so that means in this case, in the slow step, it involves 1 peroxide with iodide catalyst reacting to form our intermediate IO minus and our product water. And this IO minus, being an intermediate, will react with more peroxide and then it goes on to produce the respective reactants. Okay, now I noticed one thing, sorry, the equation is not balanced. This should be 2H2O2. Okay, can you please update? It should be 2H2O2. If not, the equation is not balanced. Okay, next. Let's look at the next question over here. The gas phase decomposition of nitrogen, dinitrogen monoxide is considered to occur in 2 steps. Okay, so this is a two steps reaction. So there should be a slow step and there should be a fast step. So the experimental rate equation is this. So your job is to identify the slow step, which is the rate determining step. So looking at the rate equation given experimentally, which step, if you assign it as a slow step, will match the rate equation? It's quite obvious. That means it's telling us that the slow step has 1 mole of N2O because the order is 1. So 1 mole of N2O, which is step 1. So therefore, this step must be the slow step. So the rate determining step is step 1. And the intermediate is something that is formed and used up. So if you look carefully, what is formed and used up, you will find that this is formed and used up. So oxygen atom is the intermediate. All right. Okay, so if you have an equation, rate equation that is like this, what can we say about the rate equation is that besides its first order, we can also describe it as a unimolecular step. So the rate determining step is unimolecular. If I have a rate equation, rate equals to K, A, B, what can I say about the rate determining step? Most of the time, we can say that the rate determining step is bimolecular because it involves 1A reacting with 1B. Okay, now what about another case whereby what happens if it's something like this? If rate equals to K squared AB, K squared A squared B. Rate equals to K A squared B. Do we say that it is a trimolecular rate determining step? Do we say that it's a trimolecular rate determining step? No. Why? Because the probability of a trimolecular reaction is low. So if we look at this, it's obviously trimolecular, right? And we know it's unlikely to happen. So it's actually telling us something. But it's telling us that it is a substituted rate equation. So that means the original rate equation involves in the intermediate, and after the substitution, this is the result of it. Not because it's a trimolecular determining step. Okay, so with that, I hope you understand mechanism a little bit. Next, we're going to move on to the last section, which is Arrhenius equation. The purpose of the Arrhenius equation is to explain the effect of temperature and catalyst on rate constant. Okay, so as mentioned, rate constant should be constant value unless certain conditions change. And what are the two factors, which will be the activation energy and the temperature? So activation energy changes when the catalyst is introduced, and temperature changes when you heat or cool a mixture. So the relationship between rate constant and temperature is given by this Arrhenius formula. Okay, so let's look at Arrhenius formula here. You'll find that if you bring this, if you take a ln throughout the whole equation, you will end up getting this equation here, which looks pretty much like y equals to mx plus c. If we let ln k be our y, and we let 1 over t be our x. So this will be your y, and this is your m, and this is your x plus c. Okay, so later when we plot a graph using this Arrhenius equation, we will expect a straight line with a y-intercept of c, and c is ln A. All right, okay, so let's look at what is A first. A is a Arrhenius factor, which is a constant again for the experiment. That constant takes into account the orientation of the reactant at the point of collision, as well as the frequency of collision. Okay, take note, you need to know what is in A because it has been tested before in MCQ. So A takes into account the orientation of the reactant as well as the frequency of collision. E is the activation energy of a reaction, which will be lowered if a catalyst is added. R is the gas constant, and T is the temperature in Kelvin. Okay, it has to be in Kelvin. So the rate constant from this expression we can see is only affected by temperature and catalyst. So you have changes in concentrations or pressure, it should have no effect. So from the expression, we can also see that if you have a larger temperature, it will result in a larger rate constant. So a larger temperature will result in a larger rate constant, and the presence of a catalyst will also result in a larger rate constant. Okay? Okay, so using the same equation just now, remember, if once we take a log or ln of it, it looks in the form like y equal mx plus c. So the activation energy from a reaction, you can actually plot a graph and get the gradient. So what type of graph do we plot? We will plot y, which is our ln k, equals to mx plus c. So we will plot ln k versus 1 over t. Okay, so we are going to plot ln k versus 1 over t. Remember, P must be in Kelvin. Now, after you plot a graph, you will find that your gradient is negative because the gradient is negative EA over R. Okay, and EA should be a positive value, R is a positive value, so the slope should be negative. Okay, so after you get a graph, find the gradient of this graph, and that gradient equals to negative EA over R. So using the gradient, so what do you do is that using the gradient, you multiply by R and equals to negative EA. And so you'll be able to get EA of any reaction through this method. Okay, now if you really want to find out what is the Arrhenius factor, then you will extrapolate the graph to cut the y-axis, and that will equals to ln A. And then from there, you can calculate A. Okay, so with that, let's look at one example. So you have a plot of ln K against 1 over T. You can see it's a negative slope. Right, so what do we do is that you can choose any 2 points and then you find the gradient of the line. So y increase, x increase, you get the gradient. After you have gotten the gradient, take the gradient, multiply by your R value, which is 8.31. R is actually a constant, and we call it a gas constant. And the value is always 8.31. So you multiply by 8.31, you should be able to get an activation energy of this reaction. Okay, so therefore, if you want to really find out an activation energy of a reaction, what are the things that you need to do is that you need to have repeated the experiment at different temperature. And you should have the corresponding K values, which is the rate constant values at different temperature. With enough points, let's say you have minimum 5 points, you plot the best fit line. And from the gradient of that graph, you find EA.